we discussed how Dyna unifies planning, learning, and acting. This unification introduced some additional concepts like model learning and search control. Today, we will take a closer look at how all these pieces fit together. In this video, we will discuss a specific instance of the Dyna architecture called tabular DynaQ. By the end of this video, you should be able to describe how tabular DynaQ works. You will also be able to identify the DirectRL, planning, model learning, and search control parts of DynaQ. Let's first discuss how tabular DynaQ algorithm learns a model. Tabular DynaQ assumes deterministic transitions. For example, when this rabbit chooses to move right in state A, there is only one outcome. The rabbit transitions to state B with a reward of 0. Likewise, if the rabbit moves right in state B, it stays in state B with a reward of 1. The left action in B always takes the rabbit to state A with a reward of 0. After the rabbit has experienced these transitions, the model knows what happens in these state action pairs. If a transition occurred once, it will always unfold that way in the future. The model can be certain about this. Let's look at the DynaQ algorithm in detail. First, we have the usual agent-environment interaction loop. In the current state, the agent selects an action according to its epsilon greedy policy. It then observes the resulting reward and next state. It performs a Q-learning update with this transition, what we call DirectRL. If we were to stop here, we would get exactly the Q-learning algorithm. This is where things start to differ from model-free methods. DynaQ will take this transition and perform a model learning step with it. To do so, the algorithm memorizes the next state and reward for the given state action pair. This works because we assume the environment is deterministic. DynaQ then performs several steps of planning. Each planning step consists of 3 steps: search control, model query, and value update. In this algorithm, search control selects a previously visited state action pair at random. It must be a state action pair the agent has seen before. Otherwise, the model would not know what happens next. Given the state action pair, we query the model for the next state and reward. We have now generated a model transition. Finally, DynaQ performs a Q-learning update with this simulated transition. The planning step is repeated many times. The most important thing to remember is that DynaQ performs many planning updates for each environment transition. And that's tabular DynaQ, a simple instance of the Dyna architecture. Let's revisit our robot friend to better understand the DynaQ algorithm. Remember, this is just a cartoon to build intuition. Like before, it starts out knowing nothing about the environment. The robot gradually builds a model while interacting with the environment. The first episode takes 184 steps. In that time, the agent only changed the value of the state action pair beside the goal. Without planning, the next few episodes would probably be just as long. Let's look at the next episode and study the impact of doing 100 steps of planning on every time step. The last time we talked about this robot, it was doing way more planning on each step. So this time around, it will take longer for DynaQ to find a good policy. After just one step, planning updated the values of 2 more states. Now the agent knows the correct actions in the final corridor. Let's run DynaQ a bit longer. The impact of planning is quite dramatic. DynaQ propagates the reward information across the entire state space. Eventually, the agent knows an effective policy for navigating to the goal from most states. The policy computed by planning only requires 18 steps to reach the goal, after just 2 episodes. That's more than 10 times shorter than the first episode. Tabular DynaQ performed many more updates to the value function than it would have without planning. DynaQ makes better use of its limited interaction with the environment. In this video, we learned how tabular DynaQ mixes planning, learning, and acting through the value function. We also studied how DynaQ updates its value function in a small grid world.